Let's take a look at another problem that shows us a pretty common recursion pattern. It's known as the max depth problem. So the idea of the depth of a binary search tree is it's the distance between the root node and any of the nodes that don't have any children. We would call those a leaf node, so the nodes that are at the bottom of the tree. Our goal is to find the longest path from a root to one of those leaf nodes. We would call it the depth of the tree. To find the depth of the tree, we have to do a recursive iteration of the tree. The goal of which is to find the furthest possible point from the root. So basically we want to iterate until we reach these none vertices, and then we want to determine how far we actually iterated to get there. This idea I often refer to as recursive counting, and it's got a very specific pattern to it that I'll show you here. So as with any other recursive function, we do this idea of a maximum depth, and we start at self.root, and we then go into our actual recursive function. And the idea here is that we say if the current is none, I'm going to return 0. Then what I'm going to do is I'm going to store the maximum left, which will be equal to recursively calling this function with current.left, and then we'll have a similar max right, which will be the same as recursively calling this with the right hand side. Then I'm going to return is the maximum of maximum left, maximum right, plus 1. Let's understand what's happening here. When these iterate through, they basically stop when we reach a none value, and it returns back 0 as a result. What's going to end up happening is that 0 is going to end up here, and it's going to take these two values, and basically when we reach the end of the left and right hand side, we're going to have like a 0 and 0 situation, so the return value would be 1. And basically each time that we move up in the tree, we get 1 added to the result of whichever is bigger, the right or left hand side. And you can see that this basically ends up counting the number of recursive calls that we've made from the bottom all the way up to the top. So basically what we end up doing is we iterate down to the left and right hand side, we iterate as far as possible, and then we're counting how many times we iterated, keeping track of which number is bigger each time. By the end of that, we end up with the longest possible path from the leaf nodes to the actual root themselves. So this sort of counting pattern is very common. Anytime that we want to count something inside of a binary search tree, we're usually going to use this sort of structure where we return 0 and then we plus 1 out of the actual return itself. So this idea is basically counting the number of recursive calls that have happened. So if I show you the idea of this, if I go ahead and print out b.maxDepth, what you'll see is we'll end up getting the actual maximum depth of this, which in this case is 3. We can verify this pretty easily through our level order. 50 is the first level of our tree. We have 30 and 70 is the next level, and then 20, 40, 60, 100 is the third level. So you see that we have 3 levels, so 3 is the maximum depth of our tree in this case. Now when we take a look at the time complexity of this, we would say that generally this looks to probably be about O(n). The reason why it's O of n is because we have to basically iterate all of the trees, or all of the nodes inside of our tree, essentially, to get to the maximum depth. So generally we'd see about an O of n time complexity for this. It wouldn't be log of n because we don't reduce down half the size of the tree on each iteration. So we have a bit of a worse time complexity than our usual binary search trees, but generally this is probably about the best we could do for our max depth iteration. So this gives you another example of a way that we can iterate through a tree using the ideas of recursion. So thanks so much for watching this video. I'll see you in the next one.